I guess the first thing we have to ask ourselves when we're looking at trigonometric substitution is why would we ever want to introduce trig functions into a perfectly good problem containing only algebraic functions? And I guess the answer to that is that there are so many kind of interesting ways that we can rearrange trigonometric functions because of their identities. And in the case of these substitutions, primarily we'll be using Pythagorean identities on trigonometric functions that allow us to convert between sine and cosine, tangent and secant. We also have other Pythagorean identities, obviously, or at least one more, but we don't tend to use that one as much because, well, for various reasons, we just don't like cosecant and cotangent as much as we like secant and tangent, and there isn't really any one reason to use one when you could use the other. So let's look, let's just jot down the Pythagorean identities that we are going to use. The first one, in the form that we'll use it, is going to be 1 minus sine squared theta is equal to cosine squared theta. And the second is 1 plus tangent squared theta is equal to secant squared theta, and we're actually going to use that one in both directions. Secant squared theta minus 1 is equal to tangent squared theta. Because we have the ability to use those identities to swap between one and the other of the trig functions, we can also see that as we move from the left side of the equal signs to the right side, we switch from having from having two terms to having a single term. And if we look back now at the integral that's presented on this page, we notice that under the radical sign we have two terms. And that's causing some difficulty for us because if we had a single term there, we might be able to simplify in some way. We might be able to do a U substitution of some kind. Actually, we might want to try a U substitution in this case anyway, but we see right away because of the x squared that when we try to make U equal to 1 minus x squared, we get du is equal to 2x dx, and there simply isn't any 2x in our integrand for us to cancel. And trying to rearrange to put things in on the top turns out to be more work than it's worth. At least, even if it is possible, it's more work than doing trigonometric substitution. So let's get rid of this stuff and go ahead and perform the trigonometric substitution that's appropriate on this example. The substitution that we want to use has to match the piece that we want to replace. So if I look here, what I'd like to replace is 1 minus x squared. And the matching piece from our three Pythagorean identities is 1 minus sine squared theta. So we need to call x something else. We're going to replace x with sine of theta. And when we do that, we need to redefine our differential notation dx as cosine theta d theta. We're going to rewrite this integral replacing dx with cosine theta d theta. and replacing the x with sine theta so that we have the square root of 1 minus sine squared theta. And now we're ready to use the Pythagorean identity that we set this up for. This is going to be equal to the integral of cosine theta d theta divided by the square root of cosine squared theta. And simplifying further, we get the integral of cosine theta d theta over cosine theta. And through this process, in this particular example, things work out as nicely as we could possibly hope. Everything cancels, and we're left with the integral of 1 d theta, or just the integral of d theta, which is equal to theta plus the arbitrary constant c. At this point, we would like to be done, but we can't very well give an answer to an integral involving x in terms of theta. So we have to find some way of going back to the correct variable, the one that we started with. And the way that we're going to do that is by using the equation for our substitution to generate a triangle. We can rewrite this equation as sine theta is equal to x over 1, and especially if we go a little bit further to write it as theta is equal to inverse sine of x over 1, we can do two things here. In the case of our particular example, we really can be done at this point. We've seen what theta is equal to. We can plug it in. The reason that we made x into a fraction x over 1 is because oftentimes we'll want to use this equation to build a triangle. And having an inverse trig function of a ratio lets us build a triangle for the chosen angle. And we don't really know what shape this triangle is going to have, except for that it's going to be a right triangle, and one of its angles has the measure theta. Based off where we put that angle theta, we know that inverse sine is looking at a ratio of opposite over hypotenuse. So the opposite side from theta is x, and the hypotenuse to our right triangle is 1. The Pythagorean theorem allows us to fill in this last side as the square root of the hypotenuse squared minus the side we know, x squared. Now we notice that this remaining side bears some resemblance. Let's scoot up just a little bit. To part of our original integrand, and it will always be the case that that will happen if we've done our substitution correctly and built our triangle correctly. So let's go ahead and finish out this problem. We know that theta is equal to inverse sine or arc sine of x plus the constant c, and that is our completed answer. We'll make some other videos a little bit later where we can practice using the other substitutions as appropriate. So thanks for watching this one. Hopefully it helped, and we'll work some more on these again.